We continue geometry stuff. Three-dimensional figures. Most things we handle in everyday life kind of have length, width, and noticeable amounts of depth to them. They occupy space. So, for now we deal with polyhedrons for the most part, and spheres and cones, and cylinders. A polyhedron is a shape made of flat faces and straight edges, so it's made of polygons. And there are two parallel bases if it is a prism. A pyramid is a polyhedron with one base. The two parallel bases in a prism also have to be identical, so they have to be congruent. They have to be the same. And you can't rotate them either, otherwise this gets really complicated really fast. So, it has to be just a translocation, and then you have the lines connecting each corresponding vertex. And these lines are parallel in a prism. A pyramid has one base, and all the other edges besides the edges of the base go up to a single vertex. Pyramids and prisms are named by the shape of their bases, such as triangular or rectangular. This shape, it's some manner of pyramid. Do we know how many edges might be hidden back there? No. So we assume that what we see is what it's supposed to be. This is going to be a triangular or triangle-based pyramid. The bases, well, the base is triangle. Actually, if this is a triangular pyramid, any of these vertices could represent the vertex, and any of the sides could be designated as the base. But for our purposes, we'll go with FGH. The faces, the lateral faces, because the base is also a face. Triangle EFH, triangle EFG, and triangle EGH. Okay, the edges are EF, EG, EH, FG, GH, and FH. The vertices, well, the vertices are, well, E, F, G, and H are E, F, G, and H. Diagonals are a figure that joins two vertices which have no faces in common. A skew line is a line that lies in a different plane and does not intersect. So for example, suppose you have a bridge. You go over the bridge and there's a water running underneath. These would be skew lines if we approximated them as straight lines, because, well, they go in different directions and they don't cross because they're in three-dimensional space. They lie in different planes, so they aren't coplanar. They don't lie along the same flat surface. In the same flat surface, so the same plane, two lines will be either parallel or intersect. Well, if you extend them to infinity, that is. Okay, draw a cube and then identify a diagonal and name all segments that are skewed to it. Okay, let's draw ourselves a cube. This is, of course, not going to win any art awards anytime soon. Okay. You should use a ruler whenever possible. Unfortunately, my equipment does not permit. So, yeah, this. A, B, C, D, E, F, G, H. Identify a diagonal. Well, from point A, you can only go to point G as a diagonal. Because point A touches these three faces, and those three faces touch every other point except G. AG is a diagonal. And it's skew to which lines? Which lines will never cross it? Oh, we see that AB, AD, AE all cross it. These three all also cross it. But the lines in the middle, they do not cross AG. So, BC, skew to BC, CD, DH, EH or HE, EF, and BF. Does this make sense? Well, how many edges does a cube have? It has 4 edges, and then 4 connecting edges. So it has 12 edges in total, and we know that 3 of them connect to each vertex of, each endpoint of AG. Therefore, those are definitely not skew. So 12 minus 3 minus 3 equals 6. And we have 6 lines identified. Wonderful. Exercises. Identify each solid. Name the bases, faces, edges, and vertices. Here, I'm going to go with name the faces refers to what sort of shape they are. The faces are squares. Okay? Because if we're being asked to name every single face, we can actually do that. Why not? C, D, F, G, and H is hidden in the back. So this is a cube. We'll be going with, for rectangular prisms, the bases are the top and bottom faces. That's usually the convention. Other types of prisms, of course, the bases are the 2 that are parallel. Bases are A, B, C, D, and E, F, G, H. G, H. Lateral faces. Lateral faces. ABHG, ABHG, BCEH, BCEH, CDFE, FE, and ADFG. ADFG. Edges. A, B, B, C, C, D, D, A, A, G, or G, A, whatever. The order doesn't actually matter. D, F, CEBH, comma, because we still got 4 more, GH, HE, EF, FG. Vertices as labeled, because technically we did name the vertices. We named them by labeling them. For everyone's time, we're gonna keep this one shorter. So it's a triangular prism. The bases are triangles. These triangles are actually supposed to be parallel. This is just presented in a 3D view instead of the usual perspective that you use in geometry, which is actually totally inaccurate. Like, that is not what the triangular prism would look like if you're standing even anything like reasonably close to it, which this diagram kind of shows. It shows perspective, which is important in stuff like art. Faces here are rectangles. The bases are the triangles. Now, the volume of a prism is base times height. The base area multiplied by the height of the solid. For cylinders, it's the same thing. Find the volume of each prism. Rectangular prism with length 6 centimeters, width 5 centimeters, and height 8 centimeters. Well, in this case, volume is equal to length, width, height. The formula is specific to rectangular prisms. Length times width is just base, so it's actually the same thing as the general formula. So length is 6 centimeters times 5 centimeters times height 8 centimeters. This brings us to 240 cubic centimeters. Now the base is a 3, 4, 5 right triangle, and the height is 33 centimeters. A 3, 4, 5 right triangle refers to this. Now, the height is 33 centimeters. That implies that the units here are centimeters. So, volume is equal to base times height. In this case, base would be 1/2 3 by 4. And then times height is times 33. So we're talking about 6 times 33. Now for a cylinder, same formula. The base multiplied by the height. So suppose we have a tin can, which is a cylinder 8 centimeters across and 12 centimeters tall with negligibly thin walls. The reason why soda cans are not in fact this shape, like i.e. just a cylinder, is because it would be too easy to crush them. The specific shape of the soda can, so all the indentations and curves and so on, those are there to provide structural strength. The side of a soda can is really easy to push in. The top and bottom are not that easy to push in, which allows soda cans to be stacked while full. So you don't need special shelves to hold them. Okay, so 8 centimeters across and 12 centimeters tall with negligibly thin walls. Find the capacity of the can. Well, that's... Capacity means internal volume. So negligibly thin walls, that means we're just using this cylinder and finding the volume of the cylinder. Base times height, and that means pi r squared times height, and that's going to be pi times 4 squared times 12. So 16 times 12 equals 192 pi. And this is in centimeters cubed. There's a problem though, that if you label your soft drink or whatever's in the can, maybe it's like canned fruit or something, or canned sardines, with this can contains 192 pi milliliters of material. Yeah, consumer comprehension is going to be a bit of a problem. So times pi, and we get approximately 603.2 centimeters cubed. Centimeters cubed also equals to milliliters. Alright, find the volume of each solid. If necessary, round to the nearest tenth. Cube with side length of 6.1 centimeters. Well, the volume is base times height, or for cubes specifically, it's the side length cubed, which means 6.1 to the third, and approximately 1 to the third, 227.0 centimeters cubed. A cardboard box with height 15 centimeters, width 40 centimeters, and depth 25 centimeters. So, we're talking about how tall it is, how wide it is, and how deep we go inside. Yeah, that's the same 3 dimensions, so length, width, height, basically. So, volume is equal to base times height, and base is the width, 40 centimeters, times the depth, which is 25, height is 15. 40 by 25 is equal to 1,000, so this is 15,000. What are the units? It's centimeters cubed. A triangular prism is put on the ground with both bases showing. So in other words, it's put down on one of its rectangular faces. Alright, the ground surface occupied is a rectangle of 15 centimeters length and 5 centimeters width. The top edge of the prism is 7 centimeters off the ground. What does this tell us? This tells us that if we look at it from the side, it looks like this. And this is 5 centimeters width, and this height is 7 centimeters. As you can see, this diagram is not to scale. Anyway, that tells us what the area of the base is. So it's 1/2 5 centimeters times 7 centimeters multiplied by the height of this prism, which is actually measured sideways, like that. If we wanted to try to make this a little bit more 3D. So 15 centimeters. So 5 by 7 is just 35 times 7.5. So it's 262.5 centimeters cubed. How about the volumes of pyramids and cones? The volume of a pyramid is 1/3 base times height. And since a cone can be thought of as an infinitely number-sided pyramid, well, it's 1/3 base times height as well. In this case, 1/3 pi r squared h. Suppose the pyramid of Khufu, i.e. the Great Pyramid of Giza, the biggest and oldest, is approximated as having a square base of 230.34 meters and a contemporary, i.e. today, height of 138.8 meters. What's the volume to the nearest tenth? That means tenth of a cubic meter. Okay then. The square base of 230.34 meters, that's a linear dimension. But it says it's a square, therefore it means the side length of the square. So volume is equal to 1/3 base times height which means 1/3 of 230.34 squared times height of 138.8 meters. 230.34 squared times 138.8 divided by 3. So it's approximately 2454748.1 meters cubed. So pretty big. Okay. Now suppose a RT2PM2 TOEFL M is fitted with a nose cone approximated as a cone of 1.9 meters diameter and 1.5 meters length. Find the volume of this cone. We are finding the nose cone's volume, therefore it's 1/3 base times height. In this case, height means the length of the cone. Okay, so 1.9 meters diameter. We're looking at 1/3 pi r squared, so 0.95 squared times height, which is 1.5 meters. Looking at 0.95 squared times 1.5. Wait, no, why am I times 1.5? I can just times 0.5. Cancel this out too. So times 0.5, 0.45125 pi meters cubed. Or if we wanted an approximation, which is rather more useful, it's about 1.42 meters cubed. So we gave the approximation after the exact value. Find the volume of a sphere with diameter 10 meters, round to the nearest tenth. Well, okay. The volume of a sphere. The formula is this. V equals 4/3 pi r cubed. Remember this well and write it down. You will find it useful later. That's assuming you don't already have it memorized. The surface area, by the way, of a sphere is equal to 4 pi r squared. Yeah, that's another story. The derivation is complex. This one, well, okay, the derivation is also complex, but yeah, you just need to memorize these formulas. So the volume of a sphere with diameter 10 meters is going to be 4/3 pi, and then 5 to the third power, which gives us 5 to the third power, 125, of course, times 500 over 3 pi. You could give that for your exact value, but it says round to the nearest tenth, which means that's basically license for us to just go straight in and give the approximation without giving an exact value. It's approximately 523.6 meters cubed. Alright, find the volumes here, if necessary, round to the nearest tenth. So 1. A hexagonal pyramid with base area 100 square centimeters and height 1 meter. A hexagonal pyramid with a base area we're given. Okay, that makes our lives easier. V equals 1/3 base times height. That's what? We have a problem here. We have different units. Be careful when you're doing questions, that sometimes they'll give you different units just to mess with you. So round to the nearest tenth. Tenth of what? Meters cubed? Actually, yes, you're supposed to go with the 1 meter because that has less significant digits. It's less exact. It didn't tell you its height exactly 1 meter, so it could be rounded. So So we have to go with the meter. That means the base would be 100 square centimeters. It's how many square meters? Yeah, that's also a problem. Look, guys, this isn't science class where you actually have to use significant digits. Because if we went with cubic meters, this would be approximately 0. Because 100 square centimeters is not 1 square meter. A square meter is 100 centimeters by 100 centimeters, so it's 10,000 square centimeters. So this would be 0.01, and then divide by 3. And if we round that to the nearest tenth, we're going to get with approximately 0. Therefore, to get any meaningful answer, this goes to 100 centimeters. Yeah. Even though, by, say, science class conventions, you would go with the least number of significant digits. So 100 times 100, which is equal to, because we divide by 3, instead of 10,000, we get this, 1/3 of 10,000. The amount of ice cream which fits strictly inside a cone with internal diameter 7 centimeters and internal depth 180 millimeters. This is 70 millimeters. So volume is equal to 1/3 pi r squared h. So 1/3 pi. And radius, well, half of 70 millimeters is going to be 35 millimeters. Squared times height, which is 180 millimeters. So 35 squared times 180, well, actually no, times 60, because we can just get rid of the 1/3 right now, times pi gives us approximately 230907.1 millimeters cubed. Of course, you don't actually generally see millimeters cubed as a consumer unit, such as, say, talking about ice cream. So if you're talking about the number of milliliters that can fit inside this cone, that's cubic centimeters. To go from cubic millimeters to cubic centimeters, you divide by 1,000. Or 230.9 centimeters cubed. Okay, suppose we have a soccer ball of 25 centimeters diameter. This question is way more straightforward than those ones. This is volume to the nearest tenth. Alright then. 4/3 pi r cubed is the formula for spheres. So 4/3 pi, and then radius is 12.5 cubed. 0.5 cubed times 4 divided by 3 times pi. So this is approximately 8181.2 centimeters cubed. Suppose we want to look at the surface areas of prisms and cylinders. The lateral area of a prism, that's the perimeter of the base multiplied by the height. Because if you unroll the lateral side, you end up with a rectangle with the length being the perimeter of the base. And then the height is, well, the height of the prism. To find the lateral area of a cylinder, you use the same formula. 2 pi r is just the circumference of the circle. You find the lateral area of a triangular prism which is 40 centimeters long, where the bases are equilateral triangles with a side length 10 centimeters. Well, the lateral area, I don't like the convention of L for lateral area because L is what I'm used to using for length. Which means that depending on convention, you can see LA a lot for lateral area. And SA is for surface area. So LA is equal to perimeter of the base times the height. The perimeter of the base is, it's equilateral triangle for the base, and the side length is 10 centimeters. 3 times 10 centimeters times the height, which is 40 centimeters. 30 times 40 is 1200. And what's the units for area? It's centimeters squared, because the units here are centimeters. Centimeters multiplied by centimeters equals centimeters squared. Find the total surface area of a negligibly thin-walled cylinder, so a theoretical shape, or a theoretical object, which has its ends open, is 3 centimeters in diameter and 12 centimeters in length. This shape sounds familiar. The dimensions sound familiar, kind of. But whatever. We'll get to that later. We can think about that later. So, total surface area. What does this mean? This means outside and inside. And negligibly thin-walled means that these areas are equal. So the area is equal to 2LA, 2 times the lateral area, which is 2 times perimeter times height. So, 3 centimeters in diameter. Pi d is the perimeter. You're looking at 2 times pi times 3 times height is 12 centimeters. So, 2 times 3 is 6. 6 times 12 is 72 times pi. 72 times pi. 226.2 centimeters squared. Those are the units. Okay, find the lateral areas and surface area of each solid. If necessary, round to the nearest tenth. A brick with dimensions 5 centimeters by 10 centimeters by 20 centimeters. Bricks, for the most part, they are considered to be thinner than they are wide. So, lateral area is equal to PH, perimeter is the biggest edge, these two, that perimeter, the biggest edges. This is the height of the brick, or the thickness. So, 2 times 10 plus 20 times height. That's 10 multiplied by 30 is 300. And the area is centimeters squared. Okay, surface area is equal to lateral area plus 2 times the base area, which is 300 plus 2 times the base area, 10 plus times 20. 2 times 10 times 20. 20 by 20 is 400. 300 plus 400 is 700 centimeters squared. Now here we have a triangular prism. And this, the lateral area, are the rectangular sides. Now, we have to figure out how long this is, right? Well, we would if it wasn't labeled for us. Well, the lateral area here is the perimeter of the base times the height. So you add these, 8 plus 17, oh, that's 25, plus 15, oh, how convenient. 40 times 10, 400 square inches. And twice the base, well, that's just 2 times 1/2 this base times the height. That's just 8 by 15 then. So that's 120 plus 400, 520 square inches for the total surface area. There's no rounding involved, and that's it. So the third one is a toilet paper roll has inner diameter 3 centimeters, outer diameter 15 centimeters, and length 12 centimeters. There are 2 lateral faces on this thing. But you can still use lateral area is equal to perimeter times height. It's just that this perimeter here is just perimeter 1 plus perimeter 2. Pi d is the perimeter of a circle, so the circumference. Therefore, for the inner tube, that surface area is going to be 3 pi times the height, pi d times h. And same for the outer side of the toilet paper roll. So we're looking for 3 plus 15, 18 pi times 12. Not in the mood to do the calculation myself. So 216 pi centimeters squared. Yeah, guys, don't round yet. Round at the very end. Like when you are looking for the surface area, right? No, the question said lateral area and surface area, so you actually do have to round here once. It's just that when you are going for the total surface area, you use the exact value. So it's approximately 678.6 centimeters squared. So this toilet paper roll and its inner diameter and the length, this is what we were dealing with in the example. A conceptual empty roll of toilet paper. How interesting. So the total surface area is equal to lateral area plus 2 base. So the lateral area is 216 pi plus 2 times the base area. The base area, well, that's pi r squared, 7.5 squared, minus the central hole in the toilet paper roll. So pi times 1.5 squared. Okay, so 7.5 squared minus 1.5 squared gives you 54. Does this work? Yeah, difference of squares tells us that it's going to be 7.5 plus 1.5 times 7.5 minus 1.5, which gives us 9 times 6, which is 54. Now, we're looking at 216 pi plus 2 times 54 pi. 216 pi plus 108 pi times 2 plus 216. So 324 pi centimeters squared, which is approximately 1017.9 centimeters squared. This is the surface of this complex shape, which is a cylinder with a smaller cylinder removed from it. Next, we have the surface area of pyramids and cones. It's still the sum of the areas of the lateral faces, so the lateral area plus the base area. The lateral faces will have a slant height, which is different from the height of the pyramid. Now suppose we look at the Great Pyramid as it was built, and it was built in units of Egyptian royal cubits, and we got around to the nearest tenth of a square cubit for the surface area. The surface area of the Great Pyramid. This actually means just lateral area. Because bottom is not it's not surfaced. It's not exposed to the surface. Right? Well, actually, we'll just do both just in case. Because why not? It's easy to add the base. So the lateral area is equal to, it's a square-based pyramid, therefore it's 4 times 1/2 base times slant height. Slant height uses L, at least in cones. So, if we have the pyramid's cross-section, you'll notice how this L is very different from H. So, what is L? This is going to be 1/2 base. We gotta use Pythagorean theorem and find L. Lateral area is 2 times the base that we're gonna be dealing with is this, the base length, times 440, and length there is going to be the square root of height squared plus 1/2 of base squared. So 280 Egyptian royal cubits squared plus 1/2 of 440, so 220 squared. You might want to just put 440 over 2 and then bracket squared, just to make it clear what you're substituting. But yeah, you sometimes have to derive the slant height for yourself. This slant height represents the actual height of the triangle that makes up the face of the pyramid. Like this is a cross-section down the middle of the pyramid. So, yeah, we're going to need a calculator for this. Plus 220 squared. 880 root 126800 square root times 880 gives us approximately an area of 313,359.1 square cubits. Square cubits. Okay then. What if the bottom counts its SA equals LA plus base. So that's 880 root 126,800. I mean, I could totally extract 100 here and get out 8,800 times root 1268, but whatever. Plus base, which is 440 squared. Plus 440 squared. Approximately 506,959.1 square cubits. Alright, what about cones? The surface area S of a cone with radius r and slant height L can be found using the formula S equals pi r L plus pi r squared. How could this be? Well, let's derive the surface area formula of cones. Okay. What is the net of a cone? Like when you unroll it, you end up with this. All right? This is a part of a larger circle. And this radius is L. Okay? Little l. This is R. What is the proportion of the larger circle? Larger circle. So pi L squared is the larger circle's area. How much of it do we have? Well, this arc length is 2 pi r, whereas this whole thing is 2 pi L. So, 2 pi r over 2 pi L of the large circle is present. So as a proportion of the larger circle's area, this portion is the part that exists in the net of the cone. Okay. Therefore, the area of this wedge shape that we have, well, the lateral side of the cone, lateral side of cone is 2 pi r over 2 pi L multiplied by pi L squared. So L goes over there, which gives you pi r L. Haha! Pi r L has been found. And the pi r squared is, of course, the circle. Pi r squared. So total SA, or sometimes just S, or just A, is equal to pi r L plus pi r squared. If you forget this formula, you can rederive it by remembering the method of, hey, this is a portion of a larger circle. How much? Oh, it's proportional to the amount of arc compared to the arc of the circumference of the entire circle. Find the surface area of each solid. If necessary, round to the nearest tenth. A square-based pyramid with equilateral triangular sides with edge lengths 20 centimeters. Okay, so for these equilateral triangles, you're looking at 20 centimeters. And this side height is equal to 10 square root 3 centimeters. Yeah, it's just a rule of equilateral triangles, or rather the 30, 60, 90 triangle, right triangle. It's 1, root 3, and 2. That's the ratios of the sides. Okay, so surface area is equal to lateral area plus base, which is 4 times 1/2 base times height plus s squared. 4 times 1/2 base times height. Brackets are important, not 4.5 times base and height. So this is going to be 2 times the base is 20 centimeters. 10 square root 3 plus 20 squared. So 20 times 20, 400 root 3 plus 400. This would be centimeters squared. Yeah, the interior and exterior of a negligibly thin ballistic cap, approximated as a cone, 14 inches across and 15 inches long. Interior and exterior. So in other words, SA equals 2LA. This ballistic cap fits over the head of a projectile, okay? It allows the projectile to move through the air more smoothly. So it has no base. Equals 2LA, and we know that one is just 2 times pi RL. It's 14 inches across, so the radius is 7 inches. 2 pi times 7. And 15 inches long. So this is 7. And this is 15. 15 squared plus 7 squared, 274, root 274. Pythagorean theorem, hurrah. So, radius is 7, and then that's root 274 for the slant length. Of course, a negligibly thin ballistic cap would not be very good. It would be entirely conceptual. It doesn't exist. So forget facilitating wind resistance or facilitating aerodynamics. Times 7 times 2 times pi. This is going to be approximately 728.0 inches squared. Yeah, round to the nearest tenth. Okay, that's good. A regular tetrahedron, so a triangular base pyramid with all faces equilateral, with edge length 10 centimeters. Hey guys, didn't we just find the slant height for these? Oh no, that was edge length, 20 centimeters. Well then, we just have to draw ourselves a little diagram again. So this is 10. This part is 5. Therefore, this must be 5 square root 3. The slant height is 5 square root 3. Or, because it says it's a regular tetrahedron, surface area is equal to 4 times the base. 4 times 1/2 base times height. And so we're looking at 2 times the base, which is 10. 10 and height, which is 5 root 3. Which comes out to 100 root 3. This is in centimeters squared. So approximately root 3 times 100, 173.2 centimeters squared. Alright, let's say we decide to dispense some salt. The surface area of this cone includes a bottom, by the way. I mean, we're going to assume it includes a bottom. So, this is a conical amount of salt. So it's pi RL plus pi R squared. What's L though? I mean, it's 1 centimeter tall and 2 centimeters in diameter. So from the side, it's 2 centimeters and 1 centimeter. This is going to be root 2 then, because it's square root of 1 squared plus 1 squared. So you're looking at pi, R is 1 times L, root 2 plus pi R squared. Therefore, that's root 2 plus 1 pi. So, plus 1 times pi. It's approximately 7.6 centimeters squared. Now for similar solids, just like you can have similar shapes, you can have solids that are also similar. They have the same shape. They might be scaled differently. Congruence is still a form of similarity. If they're congruent, they're the same dimensions as well. But their corresponding linear measures are proportional. That means if these two are supposed to be similar, this divided by this equals this divided by this. Or this divided by this equals this divided by this. So all the aspect ratios are the same. So, compare 50 over 6.25 and 28 over 3.5. 28 over 3.5 is equal to 8. 50 divided by 6.25. Yep, it's also 8. So, they could be similar. Why? Why could? Well, it's because the other sides also have this ratio. Yeah, that's kind of important. You got to make sure all the corresponding sides are proportional. Or all the supposedly corresponding sides are proportional, which would make them actually be corresponding sides. So here, 12 over 8 is not equal to 14 over 10. Therefore, not similar. Now, if you have two similar solids, you can find missing measures. For example, you can have bricks, which have a ratio of 1 to 2 to 4, and you know that they're similar bricks. One set has dimensions 5 centimeters by 10 centimeters by 20 centimeters, so 1 to 2 to 4. The bricks have 2 to 4 ratios of dimensions. This is the way I would do it. I mean, sure, you can go 7 over 5 equals x over 10 equals y over 20, but why bother? So, shortest side is means 14 centimeters and 28 centimeters on the other dimensions. Or the other measures. Okay, let's do some exercises. Determine whether each pair of solids is similar. A conical mound of salt, 5 meters tall and 10 meters across, and one 4 meters tall and 8 meters across. Well, 5 over 4 equals 10 over 8. So, similar. A tape roll and another of the same type, one half used and the other entirely used. While the central hole remains the same, but other parts of shape changed. So it can't be similar. Can't be similar. After all, if you want your amount of tape on the outside to shrink, the tape layer to shrink to a certain amount, it's not going to be 1/2. Why? Because if you used half the tape, the outer windings of the tape are longer than the inner windings, as anybody who's unrolled a roll of toilet paper, for example, can tell you. Or use a roll of tape, for that matter. So, if you shrink the thickness of the tape layer by a certain amount, you got to shrink the central hole as well, which is not going to happen as you use a roll of tape. So the proportions can't hold. So suppose a 12-inch shell and a 16-inch shell have similar external shapes, and the 12-inch shell is 60 inches long. How long is a 16-inch shell? You don't actually need to know all the dimensions as long as you're told that the shapes are similar. Similar external shapes means that the inner filler or inner structure of the shell may vary. So, let the 16-inch shell be X inches long. 60 over 12 is equal to X over 16. Therefore, 60 divided by 12 is just 5 times 16. You get X equals 80 inches. The 16-inch shell is 80 inches long. Now let's say we got a shoebox. The second shoebox has width W and height H. And the first shoebox has 35 centimeters length, 20 centimeters width, and 15 centimeters height. And it's similar to the 40 centimeter long shoebox. Okay, that means 40 over 35 is equal to W over 20 is equal to H over 15. So W is equal to 20 times 8 over 7. So that's going to be 160 divided by... Wait, do we have instructions to round? Oh, find the missing measures. Well then, that's going to be 160 over 7 centimeters. And height is equal to 15 times 8 over 7, which is going to be equal to 120 over 7 centimeters. And if you're supposed to round, or you have a convention around rounding, please apply it. Well then, that's actually it for this chapter, which was about solid shapes and their surface areas and volumes. So, see you next chapter.